All right, let's get started. This is the very last lecture in this series. And in this lecture, we are going to go along the path we established in the previous lecture on fixed point theorems. But first of all, let's look back. With no distortions, competitive equilibrium of a system and the related Pareto efficient allocation exactly coincide. So we have only one allocation that we can label as the allocation belonging to the competitive equilibrium of the system and its Pareto efficient allocation. So this is a very comfortable situation because the economy as a whole solves the problems of the individual agents. It makes things very easy because we can solve the problem from the viewpoint of the social planner with no distortions, and we can be sure that the allocation that we have as the result of the problem, it is a competitive equilibrium, and at the same time it is a Pareto efficient allocation. In chapter 17, we studied some methods, some fixed point theorems with which we could solve such distorted systems in the island model framework. So our example was the island model framework, which in a sense was very specific because we had only one state variable, which was an exogenous shock. And if you remember, in the introduction of chapter 17, Stokey and Lucas make it clear that this is a special case. So in cases where the system has endogenous state variables too, we need another approach or other approaches. And this is what we are going to do in turn. So in this chapter, in this final chapter of the book, we study models in which we have endogenous state variables. Most of the chapter is devoted to deterministic models in which the only state is the endogenous state. Endogenous, by endogenous we mean that it is affected by the decisions of the agents. So this is what we are going to do in turn. We have some good news and we have some bad news. The good news is that we don't need new fixed point theorems. So the same fixed point theorems, especially the contraction mapping theorem and Schauder's fixed point theorem, they are still available. So we will use them in this chapter very extensively. But the bad news is that there is no single or universal method for solving such distorted systems. So creativity is always needed. So what we can do in this chapter and in this lecture is that we review some productive methods with which we can have the hope of solving a distorted system. But to keep things as simple as possible, we will use a very simple model, a very simple framework, the basic neoclassical, deterministic neoclassical growth model, where there will be a tax on capital income. So this is the source of distortion. And we will try to solve the same model in different approaches. Actually, we have three possible strategies. There is an indirect approach, and if you ask me, I think this is the most exciting approach, this indirect approach. We build a distorted system, and which we want to solve, and then we build an undistorted pseudo economy, the equilibrium conditions of which, especially the first order condition or conditions, and the envelope conditions that lead to Euler equations. So these equilibrium conditions are exactly the equilibrium conditions of the economy we are interested in. And if we have this analogy, this pseudo economy, which is not distorted, we can solve this economy with the same methods as we studied in chapter 4 and 9, I guess. So it's easy to solve this problem, for instance, from the viewpoint of the social planner. And once we have solved this pseudo economy, this undistorted economy, and once we have established the channels of the analogy between the two economies, then we can have the solution to the original distorted system. The problem is that this approach is not always available. So we may not be able to find a pseudo economy through which we can study the original distorted economy. So in this case, we can have a twofold direct approach. So we may try to find the optimum policy function of the distorted system, in the distorted system, with fixed point theorems in the close neighborhood of the steady state. This is one direct approach. Or we may try to find the optimum policy function globally. So by globally we mean that not only in the neighborhood of the steady state. So this is what we are going to do in turn. First, we will go over this indirect approach through one or two examples. Then we will review the direct approaches, this twofold direct approach. So hopefully this final lecture is going to be very exciting. So let's do this in turn. Okay, so let's try to dig deeper through an example. In an economy, in a model economy, all agents have the same capital stock, except for one who has X. His budget constraint is the following, where you can identify his labor income and his capital income, and on this basis we can identify the equation that describes his consumption. So we can easily write his Bellman equation, the Bellman equation of this individual. You can see there are three state variables in this Bellman equation. The first one is his own capital stock. The second is the capital stock of the remaining agents in the economy, so all other agents in the economy. And the third variable, G, is the policy function which the agent expects other agents to follow. Okay, so G is the policy function of all other agents expected by the agent whom we are analyzing. You can see in the second half of this Bellman equation that everything everything goes like clockwork. So in the next period, the agent is going to have capital stock Y. Other agents are going to have the capital stock according to the policy function, and there is no change in the expected policy function. We can find a related policy function, capital G, which describes the optimum behavior for this agent as the function of his own capital stock, the capital stock owned by other agents, and the expected policy function. At the same time, we can have the Bellman equation of the undistorted economy where all agents has the same capital stock. Actually, both economies are undistorted. In the first economy, just to be more specific, in the first economy, there is one agent who is not typical in the sense of owning an untypical capital stock. In the second economy, all agents have the same capital stock. They are the same in terms of technology, in terms of preferences. They have the same capital stock. So optimally, they are supposed to behave in the same way, and they will be in optimum position next period if they follow the same policy function. So this is what I wrote down in the second point. If all agents have the same capital stock and the same weight in the social planner's problem, then all agents will be in the same position in the next period. As we will see in exercise 18.1, the two value functions are going to be the same, and the two policy functions are also going to be the same. Okay, so once again, if all agents have the same capital stock, we don't need to distinguish the two economies. So optimum behavior of the system can be described by the policy function of the latter economy, in which all agents have the same capital stock. Okay, let's have a distortion in this economy. There is a flat rate tax on capital income, and tax revenue is returned to consumers in the form of a lump sum subsidy. Again, just like previously, we should write the Bellman equation, but first we need to identify the income of the individual, which can be described with this equation, where we can identify labor and capital income, we can identify the tax paid by the individual after on the basis of the capital stock he owns, and we can identify the subsidy he receives on the basis of the generally owned capital stock. This income can be put into a simpler form, and on this basis we can write down the Bellman equation for the individual who owns capital stock X while other agents own capital stock K. There is no surprise in this Bellman equation, but we can easily realize that the two economies are not the same. We have this distorted economy. We have a Bellman equation for this distorted economy, and the Bellman equation of this distorted economy is not the same as the Bellman equation of the undistorted economy, even if the agent owns capital X. So value function capital V doesn't solve the second Bellman equation, the Bellman equation of the distorted system, and there is no analogy between the two policy functions. So what we are looking for is a policy function h for the individual who has an expectation regarding policy function h working in the whole economy, where just like previously in equilibrium the two policy functions coincide. So this is what we are going to do in turn. Let's try to find a solution to this distorted system.
The first exercise for the day is exercise 18.1, which is not too difficult, not too technical, but very exciting, because in this exercise we show that the solution of the social planner in the economy where all agents are identical, even in terms of the capital stocks they own, and the solution of the individual in equilibrium, where the individual has the same capital stock as any other agent in the economy. So these two solutions are supposed to be the same. So let's solve first the social planner's problem. This is the basic now classical growth model. So the Bellman equation, which is equation 1, is familiar. So this is the Bellman equation of the social planner, and we are going to solve this problem. The first order condition is quite simple. We derivate the Bellman equation with respect to the control variable, which is y, and equate the equation with 0. So here we have the first order condition. The problem is that we don't know anything about this derivative of the value function. So this is the reason why we need the envelope condition. To apply the envelope condition, suppose we have the optimum policy function. On this basis, we can write the optimized Bellman equation. No wonder the optimum policy function gives us the optimum path of the state. So here we have the optimized Bellman equation, which we can derivate with respect to the capital stock, the endogenous state. This is just a kind reminder. When we use the envelope condition, we try to find out the effects of a change in the endogenous state, and in this case we must neglect all the indirect effects through the optimum policy function. So this is the reason why we only derivate the production function, and we don't do anything with the optimum policy function. This is true of any k, even in k next period, which is y. So it is also true. All right. And we can put this and the envelope condition into the first order condition to have the Euler equation. This is the standard stuff. So there is nothing new in this treatment. Let me use time indices to be clear. So this is the Euler equation. Which is supposed to be 0 along the optimum path for the endogenous state. So this is the same as equation 2 on page 98. There is one missing but necessary restriction, which we have in the form of the transversality condition. Please remember chapter 6, where we established that the Euler equation and the transversality condition together give the optimum path for the endogenous state. So the transversality in general, this is equation 3 from the related chapter, chapter 6. In general, we write the transversality condition in this form. Here, this is so for the optimum path, it should be 0. The task now for us is to show that in market clearing, that is when the individual's capital stock is the same as the capital stock of any other agent in the economy, the individual's solution implies the same equations. So strategy that we should follow to solve the individual's problem then impose the equilibrium conditions, and to check results. We are supposed to have the same solutions. So now let's turn to the second part of this exercise, the individual's problem. Please note that we have a setting in which the individual might have different capital stock as any other agents in the economy. So we have a different Bellman equation, So what we are supposed to do is to maximize this function in terms of his private capital stock next period, which is y, while the economy as a whole follows its own optimum policy function g. Okay. from this, the first order condition is simple. We have nothing to do with these parts. We are interested in y only. And most importantly, we derive the value function with respect to the first variable. This is very important. We have 3 variables, so we must be specific all along. So this is the Bellman equation of the individual, and this is his first order condition. To have the Euler equation, next we need to have the envelope condition. So we follow the same strategy. Suppose we have the optimum policy function of the individual, and if we do, we can have the optimized Bellman equation with the optimum policy function of the individual. So this is the optimized. This is going to be the optimized policy function, optimized Bellman equation, sorry. This stands for capital stock, the individual's capital stock. Next period, just for the sake of good order. His own capital stock is described by his own policy function, and nothing else changes in this setting. If we want to use the envelope condition, we must be aware that we are interested in finding the effects of a change in the state which is in the place of the first variable. So actually what we are looking for is this function, the derivative of the value function with respect to the first variable. So this is what we are looking for. So we are going to derivate according to the envelope condition, derivate the optimized Bellman equation with respect to the state x. So this is the variable with respect to which we are derivating the optimized Bellman equation. So putting the first order condition and the envelope condition together, the Euler equation of the individual, the Euler equation of the individual, it is quite long. I'm using time indices, and I also encourage you to do so because we have so many variables, individual and economy-wide variables, that I think it's easier to apply this trick. I wouldn't say it's a method, it's just a trick. And it does no harm. if it's easier for you, and it's easier for me, so this is the reason why I'm doing so, just do what you think it's comfortable. It doesn't compromise accuracy. So in sum, it does no harm. So this is the Euler equation of the individual. So we have solved the individual's problems. We have an Euler equation on the basis of a surmised aggregate rule, and in equilibrium it turns out that, so in equilibrium where the individual's capital stock is the same as the capital stock of all other agents in the economy, so in equilibrium, in market clearing, it turns out that the agent follows the aggregate level rule. So from the Euler equation, we can write the transversality condition, the transversality condition of the individual I'm just double checking if it's correct, and it seems to be correct. Okay, and now just have a look at our strategy. So we have solved the individual's problem. So now it's time for us to impose the equilibrium conditions. So in equilibrium, the individual's capital stock is the generally owned capital stock. In this case, we have the following Euler equation and the following transversality condition. Please be aware that this is the part where we have changes. So this is the Euler equation. This is the Euler equation in equilibrium. I'm just double checking, and I think it's correct. And the transversality sorry for the background noise. I'm not sure if you can hear it. Hopefully not. Hopefully you don't. So this is the transversality condition. And it's quite easy to realize that, I'm just double checking. Yep, it's quite easy to realize that it is the solution of the social planner. So we have, again, I repeat it for emphasis, we have the solution in equilibrium. The individual's solution exactly coincides with the solution of the social planar. So in equilibrium, the two solutions exactly coincide, so the individual's policy function is the policy function of the economy as a whole, and the value function of the individual is the value function of the whole economy. So which means that if we are in equilibrium, we have that so this is what we mean by equilibrium. If the individual's capital stock is the same as the capital stock of all other agents, we have the same solutions, and this is what we were supposed to show. So we are done.
Let's go on with the problem of the individual who is atypical in terms of his own capital stock. We can easily find the first order condition and the envelope condition for the individual. This is just a kind reminder. On this basis, this is quite easy for us to proceed towards an Euler equation. So we have the first order condition and the envelope condition. And to keep things as simple as possible, we can define another function for the derivative of the value function in equilibrium when the capital stock of the individual is the same as the capital stock of all other agents in the economy. In this case, his policy function must be the policy function followed by all other agents in the economy, so the policy function of the whole economy, and we can have the first order condition and the envelope condition in this case. It's easy to realize that we have two unknown functions in these two equations. We have h as the policy function, and we have the derivative of the value function. If we can find a solution to this pair, then we can find the value function and policy function capital H. What's the strategy? The strategy is very exciting. Let's interpret this pair of the first order condition and envelope condition as if they belonged to another fictional and undistorted. This is the most important aspect of the strategy. This is supposed to be an undistorted economy that can be solved by the standard methods. And once again, as I have mentioned in the introduction, if we can solve this undistorted economy, we can infer the solutions to the distorted economy. So let's build this economy. We want to build an undistorted economy in which we have the same preferences and the same technology. However, the discount factor may be different, and the policy function may also turn out to be different. So let's make room for these differences. The idea is quite simple. If the two problems are the same, they must have the same Euler equations. So what I suggest is what I suggest is having the Euler equations for the two problems, for the distorted and the undistorted economy. And after this stage, we can check the conditions under which these two Euler equations can be regarded as the same. So here you are, we have the two Euler equations, and you can see that these two equations are quite similar. There is some difference though. First, we need to use in the undistorted problem, we need to use another discount factor. And if we identify the two discount factors, then the only difference is in terms of the two policy functions. So we can identify the two policy functions, and in this case we can just solve the undistorted problem with a modified discount factor, and we can find the policy function of the distorted economy. In this context, exercise 18.2 is very instructive. So before proceeding to other approaches, let's have a look at this exercise. It's going to be very exciting.
The second exercise for the day is exercise 18.2, which is really exciting because we are invited to build a pseudo economy in order that we could study a distorted system. So now let's lay down the basics. We can get to the economy of this exercise from the previous model, from the previous economy, where we had a tax on capital income. So this is the equation we used previously to describe the income of the agents. After expansion, we receive this equation. This is the first term is capital and labor income. The second term is tax, and this last term describes the subsidy paid by the government to the agent. The new tax, so this is the point up to which we could use our previous model. And in the new economy we are building, there is a tax on all forms, all kinds of income. So this is the equation that describes the income, taxed income, or after-tax income in this economy. After a few steps, we receive this equation, this expression. Okay, I'm just double checking, and it seems to be correct. So this is after-tax net income, from which we can describe consumption as a function of this income. And investment, next period's capital stock. So the individual the individual's problem, the Bellman equation. The Bellman equation. There is no surprise. It's a three-variable function where x is the agent's own capital, k is the capital stock owned by other agents, and function h is the policy function the agent expects to work in the economy. This is very standard stuff. There is no surprise how we are building this distorted economy. In next period, the agent is going to have capital stock Y. In next period, the economy, other agents in the economy are going to have capital stock K prime, and it is still function H that is expected to work in the economy, which can be labeled as, can be written as the outcome of function H. Alright. From this Bellman equation, it's easy to get to the first order condition. By derivating the Bellman equation with respect to the control variable, which is y. Which is equal okay, so this is the first order condition. As always, we have a problem at this point because we know nothing about the derived value function. So in order to know something, we need the envelope condition. And in order to use the envelope condition, we must suppose that function, the individual's optimal policy function exists, and on this ground we can write the optimized Bellman equation. At this point, we use the optimum policy function of the individual. Luckily, as always, we don't need to actually use this function. We only assume that it exists. It describes the individual's capital stock next period, while capital stock of any other agent follows the optimum policy function of the economy. So from this optimized Bellman equation, we can get to the envelope condition by derivating the value function with respect to the first variable, which is the state of the individual. Okay. Okay, so which is equal to, I'm trying to write as nicely as I can the equations and the expressions. Okay. And on the basis of the first order condition and the envelope condition, we can get to the Euler equation of the individual and the related transversality condition. Please remember chapter 6, I guess, where we establish the theoretical foundations that the Euler equation and the transversality condition together imply the optimum path for the endogenous state variable. Okay, so let's go along this path. In equilibrium, the individual's capital stock is the same as the capital stock owned by other agents in the economy, and most importantly, in this case, his optimum policy is the optimum policy of any other agent is in the economy. So the first order condition in this case, in equilibrium, I mean, in this case we have this first order condition. On the right we have the derivated value function, and if we introduce this notation, then we have one of our two key equations on the basis of which we can proceed to the pseudo economy. Okay, I'm just double checking and it seems to be correct. Let me highlight this equation because it's really important to us. And we have a second key equation, which is the envelope condition. So we have a complete description of the economy and its solution in terms of the first order condition and the envelope condition. And at this point, I'm also highlighting this equation. because this is the second key equation on the basis of which we are going to try to find an appropriate pseudo economy. So at this point, we will try to build an appropriate pseudo economy which is undistorted, in the hope of finding this undistorted economy, which, and this is the most important aspect of the problem, which leads to the same first order condition and envelope condition, and hence the same Euler equation. So our question now how to build this pseudo economy. Your textbook offers a solution, but I'd like to show you how to get to this solution. So we will do the brain work underlying this solution. So before forming any ideas of this pseudo economy, let's have a look at the Euler equation. The Euler equation of the distorted economy. It's a bit long, but trust me, it's going to help. Left hand side, right hand side. Here we could say simply, we could use this notation too, just for the sake of good order. Okay. All right, and let's try to find some patterns in this equation. So first of all, we have a special discount factor, and we seem to have a special production function. So these are the things we can realize. So in the first attack, okay, there is going to be a second attack. So what I'm showing you is not the final solution. This is just a step, a phase in finding the solution. But I believe, once again, I believe this fail we are going to face is very helpful, because on this basis, in the next step, in the second attack, we will find the right solution. So let's try the idea that we have this discount factor and we have this production function in the economy, which is going to be our pseudo economy, which is undistorted. So let's try to build this undistorted pseudo economy on the basis of these assumptions. The Bellman equation of this economy, the social planner of this economy. So we are just going along this path to see what we have. This is the discount factor. All right. So this is the Bellman equation. From this, we have the first order condition. It's no big deal. It's the same standard stuff. Okay, it's equal, we have an important point here, it's equal to the first order condition of the distorted economy if we have this relationship between the two functions. So let's assume this relationship between the two economies, and let's proceed on this ground to check if we have a complete and full similarity or analogy between the two economies. So on this assumption, let's proceed to the envelope condition. So once again, we are assuming that this relationship holds between the two economies, and assuming this relationship, we are checking if the analogy, the similarity, is complete between the two economies. So envelope condition, in this undistorted pseudo economy, we cannot be sure if we have the same policy function in this economy, so let's make room for differences. So this is the envelope condition from which this is the envelope condition. We simply, as always, we simply derivate the optimized Bellman equation with respect to the state, the effect of which we are checking. Okay, so here we go. Given this equation, this relationship between the two economies, we can write that this equation also holds. So it follows that the envelope condition of the undistorted economy is the following. And now we are getting to a very important point. One more step, and this is the point where we should get to the envelope condition of the distorted economy. if we go back to this highlighted equation, here is the difference. See? So we have an extra term, this one. This is an extra term in this equation, which we should eliminate. We need to find a way to eliminate this term. And so at this point, we should do some brain work. We can easily eliminate this term if this equation looked, I'm using the conditional, if it looked this way, we would have the same envelope condition as we need. Because in this case, we could get rid of these terms. So we need to form another set of assumptions in order to get to this envelope condition. So let's focus on this part of the equation. In this case, and let's think backwards. In this case, we have this relationship between the two economies. Instead of this one. So it wasn't the best possible solution. So let's have this relationship between the two economies, which means that we have this form. It is supposed to be 1. Okay. And in this case, if we have this relationship between the two economies, then the first order condition okay, and from this, and this is the final point, we have this discount factor. So by assuming this discount factor, we will get to a complete analogy between the two economies. So this is the solution, and this is the solution of our textbook. But I could show you how we could get to these assumptions. So now let's complete our analysis. Assume we have this production function and we have this discount factor. And if we are right, we will build an appropriate, undistorted pseudo economy. So the social planner's problem in this economy can be easily described by this Bellman equation. We are approaching the finish line. Now we are using this new discount factor. From this, the first order condition is very simple. Okay, it's equal to the first order condition of the distorted economy if this relationship between the two problems holds. So just like previously, we have a relationship between the two problems. So now we assume that this relationship holds, and we proceed on the basis of this assumption to check if the analogy, the similarity between the two economies holds. Okay, so in this case, we trivially have this form of the equation on this basis, which is the first order condition of the undistorted economy. So in this new economy, we also use the envelope condition, to the use of which we should assume the existence of an optimum policy function okay, from which by derivating the optimized Bellman equation with respect to the state of the individual all right, and given that we have assumed this relationship between the two economies, it follows, and this is the final step, it's gonna be obvious that our pseudo economy is appropriate. And now we can get rid of these two terms. So it works. From this, we get that this equation holds, which is the same as the first order. No, this is the envelope condition of the distorted economy. Yes, so this is what we received. Where there is one final point where the two policy functions are identical. So this is equal to the related equation of the distorted economy. So we have found the undistorted economy, which has the same first order and which has the same envelope condition, first order condition and envelope condition. So as a result, the Euler equation of this undistorted economy would be the same as the Euler equation of the distorted economy. So as a consequence, we would have the same transversality condition, and no surprise, we would have the same solution. So by solving this second undistorted economy, we would have the solution to the distorted economy, the original distorted economy. Okay, so at this point, this was the second attack. Okay, that's all. So our solution is complete.
Let's try something different in the next approach. This is a direct attack on the basis of a local approach related to the first order conditions. So we are going to work in the neighborhood of the steady state. There is a slight change in our economy. Capital income tax is thrown away, so there is no subsidy paid to the agents, to the households in this economy. So on this basis, our after-tax income function is the following. Related to the previous examples, we have two equilibrium conditions. The first order condition with the previous notation and the envelope condition. Please note the first order condition and the envelope condition are very helpful because we can proceed towards an Euler equation, and this is exactly the thing what we are going to do. There is a series of assumptions under the label assumption 18.1. These assumptions give a very specific description of the details of the technology, of the preferences. There is no extraordinary details, so I would say if you check these assumptions in the textbook, you can see that this is the standard stuff. On this basis, we are looking for solutions to the policy function and the value function on a closed set, which is capital K. Please remember, we still work with the basic neoclassical growth model, and from the very beginning of this series of lectures, we have established that the capital stock moves on this closed interval. So there is a maximum capital stock, there is a maximum maintainable capital stock labeled as capital upper bar. So on the basis of the first order condition and the envelope condition, we are going to define a function that serves as the basis of our analysis, because we can easily interpret this function as the Euler equation. In a specific case, this is a 3-variable function in a competitive equilibrium. So this is going to be our Euler equation. So we are looking for a policy function g that represents, that constitutes a competitive equilibrium, because with this optimum policy function, to all capital stocks, the Euler equation shows up where this function, with this optimum policy function, this function f is 0. So this is the Euler equation, where we interpret this function as a functional equation, because there is one unknown in this equation, and this is the policy function itself. So we are going to use this Euler equation as a functional equation, because we are looking for an optimum policy function of which we know that in the steady state capital stock, it has a fixed point. By this little detail, with this little detail, we can specify, we can narrow the set of functions among which we should look for our solution. Of course, we can interpret the Euler equation as a difference equation, which we can study with the methods of chapter 6. And moreover, we can use this Euler equation to find the steady state capital stock, K asterisk. So it's easy to find, with the methods of chapter 6, the steady state capital stock. What we are going to use is the implicit function theorem. This is a very nice application. So please realize that what we are looking for is the policy function in the second variable of our functional equation. So if the functional equation, if the derivative of the functional equation in terms with respect to the second variable is not zero, and it is not zero, it's easy to establish that it's not zero, there is a neighborhood around the steady state capital stock where if x and z, the pair is approaching the steady state capital stock, then y, the second variable, is gets sufficiently close to the steady state capital stock, and there is a continuous function describing how y changes as a response to changes in x and z, in terms of x and z. So briefly put, there is a function capital H that describes the changes in y in terms of x and z on a rectangle where the steady state capital stock is in the interval which we are working with. So this is how we try to find the policy function H for the individual. Our operator is going to be this function, what we have just established with the help of the implicit function theorem. Please realize that function H, capital H, has two variables. The first variable and the third variable of f, function f. So these two variables can be described as k and h squared. So we can use this function as the operator. This is the idea. And the fixed points, hopefully the fixed points of t, can be interpreted as solutions to function f as the Euler equation. So we can find the optimum policy functions, the optimum policy function. Okay, what we are going to do is three distinct things. First, we need to show that the operator maps from set D into set D. It is a contraction mapping with a unique fixed point. And in proposition 4, we can give a closer description of this optimum policy function. As a final step, let's try to find another approach, which is a global approach on the basis of the first order conditions. Previously, we used a local approach in the close neighborhood of the steady-state capital stock, but now we will imply stronger assumptions by which we can find a policy function not only in the neighborhood of the steady-state capital stock. This is just a reminder. In equilibrium, which is implied by the optimal policy function, we have this Euler equation, and we are trying to find a solution in the form, a solution to this Euler equation in the form of an optimum policy function. In assumption 18.2, we bring in the additional criteria regarding technology and preferences, while assumption 18.1 still applies. Note that on page 555, we have a quite long list of attributes with which we narrow the set of possible solutions to the Euler equation. These attributes regard, for instance, monotonicity of the policy function, or more importantly, these assumptions exclude damped oscillations around the steady state, by which I mean that from under the steady state capital stock, we cannot get to above the steady state capital stock, and from above the steady state capital stock, we cannot get below the steady state capital stock. So there are no oscillations in this system. In the last on the last few pages of the chapter, Stokes and Lucas give a short description of the application of this method to stochastic problems, and there they highlight that this no oscillation assumption cannot hold in that case. It cannot hold in stochastic environment. As a result, we have figure 18.1, which is a close description of the functions with which we work. On this basis, on the basis of the Euler equation, we define an operator, which is the equilibrium condition we use, and we want to use Schauder's fixed point theorem to argue for the existence of a fixed point of t. So the rest of the chapter is built around the application of Schauder's fixed point theorem. So simply put, we must check if the assumptions underlying the fixed point theorem hold. So we show that t, the operator, is well defined, by which we mean that in each round of iteration we have a unique solution. So we must show that we have the appropriate monotonicity for this equilibrium condition. So the left-hand side and the right-hand side must have appropriate slopes, strictly increasing and strictly decreasing, because in this case, if we can show it, and we can show it, there is only one point. There is only one point of intersection that ensures a unique solution to each round. In each round of iteration, if we have an initial guess to function h, then the operator maps the set f into itself, and last but not least, the operator must be continuous, and the family of functions that is created by the operator in rounds of iteration, this family of functions must be equicontinuous. It's a bit tricky when you follow the mathematics. we show that f is uniformly continuous in the Lipschitz condition. Please remember that equicontinuity is only a version of uniform continuity, and uniform continuity can be demonstrated in many ways, one of which is the Lipschitz condition. So f is uniformly continuous in the Lipschitz condition, and given the fact that the operator maps set f into itself, then the resulting set of functions is also equicontinuous. So we can apply Schauder's theorem to this problem. So we have a fixed point by the use of the operator we defined, and we have an additional result. T, the operator, is monotone, so by converging from opposite directions in set f, we can find, and if we find the same fixed point, so if we start an iteration from the opposite directions in f, and if we find the same fixed point, then we can say that the fixed point we find is unique. So on this ground, we can argue for the uniqueness, not only for the existence, but for the uniqueness of the fixed point. We can do this because set f has a higher and a highest and the lowest point, so we can start iteration from opposite directions, and if these iterations meet somewhere in between, then the fixed point is unique.